Let me tell you about these recursive graphs my kid came up with. In its simplest form, this is not the simplest, we need 3 bytes of information to define a rule. Let's take, for example, 110, 001, 111. This defines our rule, our behavior of the graph. It's a directed graph. We start with a single node, an edge coming in, and now the rule tells us what happens. The first byte tells us what happens to a node that has 1 branch coming in, so this is the case now. This tells us, okay, we have 2 branches going out, 1 left, 1 mid, so we will get something like this. And then in the next step this continues. We have 1 edge coming in with both of them, so 1 left, 1 mid. So now here we have 2 branches going in, so now something different happens. There we have 1 branch going right. Here a kind of a crossing, that doesn't matter. Now here we have the first case of 3 branches going in. Let's have a look at our rule. For 3 branches going in, we have 3 branches going out in all directions. We messed up the distances here a little. Doesn't matter. It's alright. Okay. Let's make like 2 more rounds. See what this looks all in all. We have this tree coming out of it. Okay, now let's add some complexity with a new rule. This time it will be a 6 byte rule. Let's go with 001, 100, 011, 011, 111, 111. This is our rule. Again, we'll start with 1 circle, 1 node. We assume there's 1 edge coming in there, so we have the rule, okay, there's 1 going right. But now, instead of drawing another circular node, I'll draw a square. This is the rule for circle nodes. This is the rule for square nodes. So now we have a square with one edge going in. This tells us, okay, we have going one up, one right. And it's now circles again. So circles and squares will just switch regularly. Now again we have one edge coming into a circle each time, so one right. Now one up, one right. Here we have the go left rule. No, those need to be squares, sorry. How does it look like? Something like that. That's now a rather asymmetrical rule, and we get some interesting behavior with like the trend to go right, but then here it will start to go left again. And of course I like the holes. For very many rules we get Sierpinski-like holes, perhaps to no surprise at all. Let's maybe do one more shape. So we have 3 shapes taking turns, 3 types of rules. Let's see. Marking the rule which is which. For the circle we'll do not 1 1, not 1 not. For the square we'll have 1 1 not 1 not. And let's do a triangle. For that one we'll have not 1 not 1 not 1. So let's see what happens. I have my starting node here. 1 up, 1 right. Squares. Left, 1 up, triangles. And now those 2 die and only that one continues. Circles. you've already noticed now that we have started repeating. Like here, I think it starts here. Here we have 2 triangles that will continue, the other ones stop, and here again. So everything that comes after here is the same as that comes after here. So we have now a regularly continuing graph. So first it looks rather complex until we fall into a periodic pattern. I have been on the hunt for a graph that starts with interesting patterns but then ends up terminating. My kid found some versions when like altering the rules some more. Like one version he did is that he had special rules for the bounding nodes, like the leftmost and the rightmost node, so that can control for the growth, that it won't grow too much. Another version that he did is with different colors, so that he has some special rules for when the edge comes in like from the left, then he will change color, and each color has its own set of rules. Here we see his notation for those special rules, and here he has a tree that will terminate because for black the rule is always terminate no matter what happens. So it feels like a bit of a cheat, but he achieved the goal. Anyway, there's plenty left to explore. I'll sure come back to those graphs with code at some point. But for now, thanks for listening.